Welcome back to Statistics. I'm Dr. Jeff Groh. Today we're going to talk about correlation and regression. Intuitively, two variables, x and y, are linearly correlated if the xy scatter plot is more or less linear. It'll be positively correlated if the slope of the line of best fit is positive. It will be negatively correlated if the slope of the line of best fit is negative. So this side is positive correlation and this side is negative correlation. The value of the slope is irrelevant, just that a positive slope would be positively correlated and a negative slope would be negatively correlated. Consider the following. Let's suppose we have data points. I'm thinking of quite a few data points. This will be a collection, say as I goes from 1 to n. So this will include x1, y1, x2, y2, and a bunch of different points. Now, these points will have a mean for the x's and a mean for the y's. So consider the following product. xi minus x bar times yi minus y bar. If both xi and yi are greater than the means, then this will be positive. If both xi and yi are less than the means, then you'll have a negative times a negative, which is still positive. If they're both greater than the mean or both lesser than the mean, this product will still be positive. However, if one of them is greater and the other one lesser, then you get a negative. Thinking about our scatter plot, suppose we have a scatter plot of points. It goes something like this. We'll have some mean point, x bar, y bar. If you choose a point over here, the x coordinate of this point will be bigger than x bar, and the y coordinate will be bigger than y bar. And so you'll get a positive. Consider a point over here. The x coordinate will be less, and the y coordinate will be less than the mean, and therefore this too will yield a positive product. On the other hand, if the slopes went down like this, you'll have some mean point x bar, y bar here. Any point over here will have an x value that's less, but a y value that's more. So you will get a negative product on any such point. And the same thing over here, a negative product for those points. So these products are picking out the trend of going up or the trend of going down as to whether these are positive or negative. We're going to make the following definition. This is the Pearson product moment correlation coefficient, and it's denoted by R. It's the sum over all of your data values. Now the products that you're going to have are your x minus x bars over the standard deviation for the x's times y minus y bar over the standard deviation for the y's, all divided by n minus 1. And so you're getting these products, these x minus x bars, y minus y bars. But we're rescaling those with this standard deviation and then dividing the whole thing, more or less taking an average, by dividing by n minus 1. Yes, we're not really taking an average because we're not dividing by n. We're dividing by n minus 1, but that's the effect. So what does the correlation coefficient, which we'll refer to this kind of informally, what does it measure? It measures the tendency for the data to lie on a line. If the data lies exactly on a line, it turns out that the correlation coefficient will be 1. R equals 1 if exactly on a line. If your data is in some big nebulous blob, you could get a correlation coefficient of 0. The correlation will be negative 1 if the data lie exactly on a line with a negative slope. So R equals 1 if exactly on a line, positive slope. R equals negative 1 if it's exactly on a line with negative slope. And it can be anywhere in between. But this R value will only take values between negative 1 and 1. Some notes about the correlation coefficient. It is sensitive to outliers. Yes, if you have data that's more or less like this and then something way over here, that can throw that linear relationship way off. It measures the strength of the linear relationship between x and y. And lastly, if you swap x and y as coordinates, then R is unchanged. So swapping the x and y coordinates of these points will literally do nothing to affect the correlation coefficient. R will be the sample correlation coefficient. Rho will be the population correlation coefficient. Rho. This is the lowercase Greek letter rho. There's the lowercase and the uppercase Greek letters rho. We will perform hypothesis tests for the correlation coefficient. In particular, our null hypothesis will often be that the population correlation is 0, uncorrelated, no linear relationship. Our alternative hypothesis will be rho is not 0, so there is a linear relationship. We'll have critical values for R in table A-6 in your book. This is on page 740. Note, it's very important to note that correlation does not imply causality. Two variables can be very linearly correlated and yet have no causal relationship. There may be some other variable that is the cause of both. Also, do not try to correlate averages. There's too much compression in the data when you take these averages. Also, no linear relationship may leave open the possibility of some other relationship. The data may be exponential, it might be logarithmic, it could be any number of things, sinusoidal. So there are a lot of different possible sorts of relationships other than just a linear relationship. Before getting to the examples, I will also want to talk about linear regression. Here, the goal is to find the best line that fits this bivariate data. Bivariate meaning has both x and y. So, what's the best line? We have something called the least squares line of best fit. This will give you a line y equals mx plus b with a slope of m, and b is the y-intercept. So b is here, m is the slope, and we have formulas that will give you, given a collection of points like this, the slope and the intercept. The slope of the least squares line of best fit is n times the sum of x, y's. That's where you take the product of each of the coordinates x, y's in your data values, minus the sum of the x's times the sum of the y's, divided by n times the sum of the x squareds. That's where you square the x coordinates of the data values and add them all up, minus the sum of the x values squared. That's where you add up the x values and then square the result. These are not the same thing. The y-intercept is found with a similar formula. First, you add up the y's times the sum of the x squareds minus the sum of the x's times the sum of the xy's, all divided by the same denominator as before, n times the sum of x squareds minus the sum of the x's quantity squared. I have to be honest with you. In almost cases, we'll calculate this line using technology. For our first example, we'll give you some data. First of all, shoe print size versus height of the individual. You would think that the taller a person is, maybe the bigger their feet are, but the relationship won't be perfect. There are some fairly short people with very big feet and fairly tall people with very short feet. So this is the data that we're going to have. 29.7, I suppose that must be in centimeters, 175.3. The next one, 29.7 also, and then 177.8, 31.4 versus 185.4, 31.8 and 175.3, and then 27.6 and 172.7. I want to know a few things about this. I want to know R. I would like to do a hypothesis test, whether or not this is unrelated or not. The null hypothesis will be that the correlation coefficient is 0 for the population. Our alternative hypothesis will be that the correlation is not 0, that there is some linear relationship. So first, we'll calculate the correlation coefficient. Second, we'll perform a hypothesis test on whether or not there is a linear relationship. And third, I want to know the least squares line of best fit. And we'll use technology to do all of these things. First, I'd like to enter the data. So I'm going to go to Stat, and I'm going to edit my lists. Let's see, we'll clear this list, we'll clear this list. The first list was 29.7, 29.7 again, 31.4, 31.8, and 27.6. And then for our next list, it was 175.3, 177.8, 185.4, 175.3, and 172.7. So we have two lists entered here. I'll do second and quit to get out of that. Next, I would like to go back to Stat, and here we're going to do tests. I'm going to scroll up from the bottom and do a linear regression t-test. Linear regression t-test, close to the bottom. We're going to use list 1 and list 2. We mentioned the alternative hypothesis will be that they're uncorrelated, though we should probably do the test with them being positively correlated with the last option as well, because that's a more reasonable alternative hypothesis. If we scroll all the way to the bottom, we can find the correlation coefficient for this data is 0.48. 0.48 is the actual correlation coefficient. The kind of line it's giving you is y equals a plus bx. So with the technology that I have here, b is the slope that we've been calling m. A is the y-intercept that we have been calling b. So we have the least squares line of best fit. We'll write that down in a minute. But we really want to look at the hypothesis test. So I'm going to go back up to the top. The p-value is 0.41 with the two-tailed test that we've given here. 0.41 is a lot bigger than a significance level of, let's say, 0.05 or even 0.10. And so we will fail to reject. The t-value is even less than 1 standard deviation from the mean. So we do not find a linear correlation. Why did we not find a linear correlation here? Probably because we only had 5 data points. Very few points. We need more data points to be able to come to a better conclusion. In our next example, we're going to look at galaxies. Suppose that d is the distance to the galaxies in megaparsecs, and v is the recessional velocity. That's how fast the galaxy is moving away from us, or apparently moving away from us, in kilometers per second. We're going to make a table here. Suppose that a galaxy is 29 megaparsecs, and the recessional velocity is 2020. 24 megaparsecs, 1900. 39.1 and 2640. 19 and 1200. By the way, I should mention that Edwin Hubble noticed all of these. In fact, it had been common knowledge, I guess, from astronomers for a number of years, even before him. But he noticed a linear relationship between the distance to the galaxy and how fast it seemed to be moving away from us. It wasn't a perfect relationship, but it seemed to be a linear relationship. That the farther the galaxy was, the faster it seemed to be moving away from the Earth. This movement was actually explained by Einstein later with his general theory of relativity, the idea that space-time is stretching. It's not that the galaxies are necessarily moving faster and faster away from us the farther away they are. It's just that the universe is stretching more and more, and that causes them to appear to be moving faster away from us the farther away they are. 4.2, we have 300, 41, and that's 2800, 20, and 1120. We're not done, we have more data. 12 and 870, 10 and 750, 9 and 680, 22 and 1510, 35 and 2300, 20.8 and 1490, 28 and 2414. Is there a linear relationship? What is the correlation coefficient? And can we calculate the least squares line of best fit? Typing the data in again, I'll go to Stat Edit. I'll clear the lists that I have and enter these values again. So we have 15 data points. This is actual data that has been collected about galaxies. Galaxies consist of 100 billion, 400 billion, a trillion stars. And you sometimes can see, say, the Andromeda Galaxy with a pair of binoculars as a kind of a fuzzy little white milk slud on the space sky. So now we'll go back to Stat and we'll do the tests. Scrolling up, linear regression t-test. That's what we want to do. Let's choose an alternative hypothesis that the correlation is positive. And you can see the p-value is incredibly tiny, and t is over 16 standard deviations from the mean. So this number, the p-value being so tiny, we definitely will reject the null hypothesis that there is no linear relationship, and we will then take the alternative hypothesis that the relationship is positively correlated. If we go down to the bottom, we'll see a correlation coefficient of 0.98. This is a very high correlation. Keep in mind, this is actual data for galaxies that have been collected. For the least squares line of best fit,
Remember, b is the slope and a is the intercept. So the slope here will be 69, a 19.8.
The alternative hypothesis, first of all, the null hypothesis is that the correlation is 0. The alternative hypothesis will be that the correlation is positive. And so that's the way we'll approach this for this problem. We find that the correlation is 0.977, very close to 1, very close to a linear relationship here. What is the p-value on this hypothesis test? We're getting 1 times 10 to the negative 9. Wow, that's 8 zeros and then a 1. That's a very small probability, very much less than any reasonable significance level that you wish to specify. And so we will reject the null hypothesis. It appears that the correlation is positive. There is a test statistic that we can use for these hypothesis tests, but you need to know the correlation coefficient. It's the correlation coefficient over the square root of 1 minus the correlation coefficient squared divided by n minus 2. This is a t statistic with degrees of freedom equal to n minus 2. We can find the critical t's. Table A3 gives us the critical t's. The degrees of freedom equal to 12 with the level of significance of 0.01. The critical t is 2.718. That's definitely way smaller than the t value that we have, and so we reject the null hypothesis. Alternatively, we can use table A6 with 12 degrees of freedom and a level of significance of 0.01. There's a critical R value, 0.708. If the correlation coefficient has any number bigger than 0.708, then we reject the null hypothesis. Well, our correlation is 0.977, and so that's bigger than the critical correlation, and so again, we reject the null hypothesis. So let me be clear, there are two ways of going about this. You can just calculate the correlation coefficient, and you find a critical correlation from table A6. That allows you to determine whether or not the correlation is 0 or not. Alternatively, once you've calculated the correlation coefficient, you can calculate the t. You can look up the critical t in table A3. So that gives you two methods for conducting the hypothesis test. As we saw with these galaxies, the distances versus recessional velocities, we can use, say, the distances to predict what the recessional velocity will be for a given galaxy. What are the conditions for using regression for predictions, much as we did with the last data? First, the scatter plot must fit the regression line reasonably well. Second, we'll only use the regression line for predictions if the hypothesis test indicates that rho is not 0. So only if you reject the null hypothesis that the correlation is 0. Third, do not extrapolate. If your data lies in here, don't make predictions about what happens over here. You can extrapolate too far beyond the data and the results will be meaningless. Maybe something else will happen farther along. Maybe something will take a turn. Maybe it'll bounce and go some other direction. Who knows? Lastly, if the regression line is not appropriate, then the best estimate for prediction is the sample mean. If our sample data looks something like this, we might have a point x bar, y bar, which is the mean of the x's and the mean of the y's. Each of these has coordinates x, y. We might have a least squares line of best fit. Let's suppose that this is the point xy. This point is the predicted point for that given x. We'll have x and then y hat. Y hat will be the predicted value using the least squares line of best fit to calculate that y hat. I've written some data down for shoe print size versus height, and I'm going to enter these as lists. We have 31.3, 29.7, 31.3, 31.8, and 31.4 versus these heights of 180.3, 175.3, 184.8, 177.8, and 182.3. Are these linear related? Stat will do tests. Linear regression t-test. We'll have as the alternative hypothesis that rho is positive. There's a increasing relationship with height along with shoe size. We get a p-value of 0.16, so we fail to reject the null hypothesis that these are not linear related. However, let me add 2 more points to this data. (30 and 177.8, 28 and 170). Now, when we conduct our test, linear regression t-test, the p-value is 0.008, which is less than alpha equals 0.01. And so in this case, with this new data, we'll reject the null hypothesis that the correlation is 0 and accept then that the correlation is positive. The correlation value, the correlation coefficient, at the very bottom here is 0.846, rounded to 3 decimal places. The least squares line of best fit will have a slope of 3.036 and an intercept of 85.6. 739. The t value that we get is 3.5467, which is pretty big. 3.5 standard deviations above the mean. We definitely expect to reject the null hypothesis with a t value that big. For a line of regression, we'll have data points but we'll also have this predicted y. That's what you get when you plug x in up here. What we're defining here is called the residual. It's the actual data y value minus the predicted y value. So on our data, we'll have a least squares line of best fit at a particular x value going up to this point xy in the data. We'll have this point xy hat. It has the same x value, but the data value and the predicted value aren't necessarily equal. Their difference is called the residual. Sometimes plotting a graph of the residuals tells you something more about the data.